Welcome to the second part of the YouTube series, Creating Your FEM Right the First Time. In this part, we're going to cover the good FEA practices to build a reliable and accurate model. So, I'm going to dive into the practical aspects of FEM creation, including planning your work, selecting the right solution type, defining appropriate boundary conditions, and meshing techniques. This part is packed with essential tips to help you create robust and accurate models right from the start. And I will conclude this part with the 14 questions you should be able to answer before you begin the modeling process. First, plan the work and keep it simple. I like to say that developing an FEM is like playing chess. To develop a reliable FEA, you must first anticipate the problems, predict the behavior, and adapt your strategy. We know that anticipating the potential issues when building a complex FEM is not easy. So it is the reason why planning is the key. Without planning, you may encounter problems you won't be able to solve without diminishing the intrinsic quality of your model. So the main objective of an FEA is to understand the system. So you need to define the goals of the simulation as precisely as possible. So before to start modeling, I recommend you answer the 4 following questions. First, what should be captured by the FEA? Which quantities are to be calculated? And which solutions are you going to draw from the solution or from the simulation, I should say? And finally, what is the required precision of your calculation? The most common error made in FEA simulations is setting up a simulation without answering these questions before to start the modeling and without having a clear goal in mind. So I recommend you never set up a model just to see what happens or to see how stresses are distributed. A precise definition of all the objectives is important for defining the modeling techniques and the solution you will use. This will influence many of the assumptions you will make during the building process of your model. For example, different modeling techniques are used to model linear and nonlinear problems. There are also different modeling techniques for capturing peak stress in particular regions of a component versus the stiffness of the wall component. So when you jump to the FEM setup, keep the model as simple as possible. For example, if you only need to know whether a yield stress is exceeded somewhere in a metallic component, it is much easier to perform an elastic calculation and check the von Mises stresses with the post-processor. You don't need to go with a full nonlinear solution. At the beginning of a project, a design is usually preliminary and even incomplete. So, the FEA analyst supports the design team in defining the concept. At this point, it is best to keep the FEM simple. It will be easier to implement modifications and to run the threat study. However, take care to not oversimplify the model to the point that the critical effects are missed. At the beginning of the project, use coarse mesh with simplified modeling techniques. Once the design is mature or enters the final phase of the design process, the FEA analyst must validate the concept. So this final verification requires more detail, but you have to add the complications step by step. Setting up the model in steps has two advantages. The first is if errors occur, it is much easier to find out what caused them. And also, understanding the behavior of the system is easier because you understand which addition caused which change in the model behavior. When running a finite element analysis, one of the first decisions you must make is about the type of analysis that you're going to run. The objective is to define the type of analysis required to capture the real effects. Asking the proper questions may be the most difficult thing in FEA, okay? But you are the only person that can describe the problem you wish to solve. So, you will have to choose between static, buckling, modal, dynamic, linear, or nonlinear solutions, right at the beginning. The first question to answer is it a static or a dynamic problem? Dynamic simulations require the presence of inertial forces and changes in kinetic energies. If inertial forces are irrelevant, run a static solution. If the loading is constant over a relatively long period of time, and if the loads are applied gradually, a static analysis will give you the right answer. As a rule of thumb, a simulation is static if the excitation frequency is less than 1/3 of the lowest natural frequency of the structure. Always remember that in a dynamic analysis, you will need to define damping to obtain realistic results. So make sure you can estimate or measure the damping of the structure of the system you want to analyze. Then you have to decide if you run a linear or a nonlinear solution. If you are planning to run a nonlinear analysis, you should answer few questions to decide if you really need to or if a linear analysis will do the work. You have to keep in mind that a nonlinear analysis requires more resources in terms of disk space and computing time. So it's very important to ensure that it is really necessary. I like to say that it is better to run a nonlinear analysis unnecessary than to ignore the nonlinear effect when it is required, because this can lead to serious design errors. But if you run a nonlinear solution while there is no nonlinear effects, the nonlinear solver will give you the same answer as the linear one. Okay? However, if your structure exhibits significant nonlinear effects, the answer using a linear solution will be wrong. Here are 6 questions which will help you deciding if you have to run a linear or a nonlinear analysis. The first question: is the stiffness of the structure changing when a loading is applied? If the answer is no, it is a linear problem. If the answer is yes, it is a nonlinear problem. Another question is, are the strains in the model less than 5%? If you answer yes to this question, it is a linear problem. If you answer no, it is a nonlinear problem. Are the loads and boundary conditions constant in magnitude and direction during the analysis? If the answer is yes, it is a linear one. If the answer is no, it is a nonlinear problem. Is the behavior of the structure independent of load history? If yes, it is a linear problem. If no, it's a nonlinear problem. The other question you have to answer is, are the stresses of the model exceeding the proportional limit? If the answer is no, it is a linear problem. If yes, it is a nonlinear one. The last question you have to answer is, the structure exhibit stress stiffening? By stress stiffening here, for example, I mean tension bending coupling, where the bending stiffness increases because tension is transferred in membrane. Okay? So if you answer no to this question, it is a linear problem. If yes, it is a nonlinear one. If you are interested to capture the linear stability of your structure, you have to run a linear buckling analysis. But before, you have to verify that your problem is working in the small displacement domain and that yielding does not occur. If not, you absolutely need to run a nonlinear buckling solution. Keep in mind that linear buckling analysis will compute only the buckling factors with the associated mode shapes. It will tell you if your structure is stable or not with the associated reserve factors, the margins, but not more. If you need the displacements or the stresses at buckling, or if you need to capture what will happen after buckling, you need to run a nonlinear solution. Finally, you need to define if you need to run a modal analysis. You can run a modal analysis for the following reasons. First, if you need to define the natural frequencies at which a structure tends to vibrate in order to avoid resonance. Also, if you need to understand the behavior of a structure under dynamic load before to run a dynamic analysis. It is important in that case to run a modal analysis. Finally, you can run a modal analysis if you want to find possible modeling mistakes, like missing connections between components, constraints incorrectly defined. In that case, the modal analysis is very useful. Another very important topic when building the model is the control of the inputs. A simulation cannot be more precise than its input data allow, so you must control the inputs. Critically consider how precise your material data really are. How large are the uncertainties? If you don't know, you can vary the material parameters, for example, to see how results are affected by the uncertainties. But be careful when computing material data. If data have been derived using theoretical equations, for example, a Ramberg-Osgood law for the plasticity, the real behavior may strongly deviate from it. So if the tested stress strain curve is available, use it instead of the theoretical one. Also, check the precision of external loads. If loads are not known precisely, use a conservative estimate. If you vary parameters, for example, the geometry of your component, it's very common to do that, make sure that you correctly consider how external loads are changed by this geometrical variation. The frictional behavior or friction coefficients are also frequently unknown. Check the parameters you use and also check if the friction law you are using is correct, because there are many friction laws that you can consider in a nonlinear material problem. Let's talk about choosing the element type. It's very important, and it's often a crucial step in creating a finite element model. Never accept the default choice of your program, of your software, without thinking about it. carefully check which type of elements are available with your library of elements related to the software you're using, and make sure you understand how a finite element simulation is affected by the choice of element type. You should understand the concept of element order and integration points, also known as the ghost points. Learn the most common errors caused by an incorrectly chosen element type. A typical example is the shear locking, for example. To select the right elements from your library of elements, you must predict your structure's behavior. The critical issue when selecting elements for your FEA, your simulation, is knowing how the structure will behave before you begin your modeling work. You must understand the load path in your structure to be able to select the right elements. Remember that you should not use FEA to predict the behavior of your structure. In fact, you must do the opposite and be able to predict the behavior of your structure and in order to build a reliable finite element model. If you do not have a fairly good idea of how the structure will behave, you won't be able to select the right elements for your simulation. So to make sure you select the right element, experiment your library of elements before to use it. If you are not familiar with an element, experiment it by doing a very simple model. This practice will give you a better understanding of an element's capability and limitations before using it in a large production model. Here are a few guidelines for a correct element choice. Use 2D elements instead of 3D solid elements for thin wall structure. By thin wall structure, here I mean structure having width to thickness ratio, greater than 10 to 20. When using 2D elements, make sure to use the correct formulation because shells and membranes look similar, but they behave differently. Do not use fully integrated first-order elements if bending occurs in your structure. Consider a reduced integration. In contact problems, first-order elements can improve convergence. If elements distort strongly, first-order elements are better than second-order elements. Also, avoid triangular or the tetrahedral first-order elements. Here, I'm talking about the triad3 and the tet4 elements because they are much too stiff, especially in bending, and they produce wrong results. For the triad3, just use them in the transition regions, far from the regions of interest. For the tet4, don't use them, use the tet10. For 3D solid element, 3D solid meshing, prefer X elements, the X8 or X20. If X meshing is not possible, and very often it's not possible when the shapes are too complex, as I said before, prefer the tet10, second order hexahedral element. They give very good results in the critical regions if the mesh is converged. Do not mix elements with different order, because this can cause overlaps or gaps forming at the interface, and it gives wrong results. When incompatible elements in terms of degrees of freedom are used in the same model and are connected together, make sure you manage this incompatibility at the interface using extra elements or interpolation rigid body elements. The typical example is a connection shell solid or beam solid. Even if it is possible to mix reduced and fully integrated elements of the same order, it is not recommended practice, okay? Since they differ in stiffness, spurious stress or strain discontinuities may result. Understanding meshing is an important part of the simulation process because it will drastically influence the results obtained from your finite element analysis. Let's have a look at the major guidelines for meshing. A fine mesh is needing where gradients in stress and strain are important. For thin wall structures, mesh with 2D elements at mid-plane for metallic and at the OML for the composite. A preliminary simulation with a coarse mesh may help to identify the regions where a greater mesh density is required. Keep in mind that the required mesh density depends on the quantities you want to extract and on the required precision. For example, displacements are often calculated more precisely than stresses or strains because stress and strain involve derivatives. Check the shape and the size of the elements, okay, with your pre-processing software. The inner angles should not deviate too much from those of a regularly shaped element. You should use the typical check like the Jacobian, okay, the Jacobian ratio. It is a very powerful check that you can do with your pre-processing software. So use the tools available in your FEA pre-processing software to highlight the critical elements, okay? Avoid badly shaped elements, especially in regions where high gradients occur and especially in the regions of interest. If you use local mesh refinements, the transition between regions of different element size should be smooth, okay? As a rule of thumb, adjacent elements should not differ by more than a factor of 2 or 3 in their area or volume. If the transition is too abrupt, spurious stresses may occur because a region that is meshed finer is usually less stiff. For the mesh transitions, never create a mesh transition in a region where there is a stress gradient. Never create a mesh transition in a region of interest. Respect the physical interfaces. If you wish to capture the peak stress or strain in a region with a stress concentration effect, I should say, or high stress or strain gradient, you must perform a convergence study to define the appropriate mesh density. When performing mesh refinement, prefer a local refinement instead of a global element size reduction. This approach permits to limit the number of degrees of freedoms. Always keep in mind that the computing time is proportional to the square of number of degrees of freedom. 3 last guidelines that I want to share with you about meshing is avoid the mid-side to corner node connections between elements. Adjacent element should have connected mid-side nodes. It's very important. Avoid back-to-back triangles and avoid also the triangular elements at the edge of holes, as illustrated here on the screen. Do not create mesh transitions in fillet. Make sure that they are on the planar surfaces. During the process of creating an FEM, defining the boundary conditions is the stage at which many engineers make incorrect assumptions. The topic of boundary conditions is less understood by FEA beginners, but it is not uncommon for experienced engineers to also have difficulty properly defining them. Boundary conditions have a major impact on the results of an analysis, and a small mistake when defining them can make the difference between a correct and incorrect simulation. So let me share few guidelines with you. First, use a strategy to define your boundary conditions. Predict how the model will behave using your engineering judgment or test results or previous analysis. But your engineering judgment will be your best tool. Ensure that the set of boundary conditions, and here by boundary conditions I mean constraints and loadings, reflect the real life. Make sure that all parts of the model are constrained so that no rigid body motions are possible. After computing the model, take the time to ensure that nodes were constrained as you expected using your post-processing software. It's as simple as doing a deformation plot, okay? As you see here on this slide. If loads are changing in direction or magnitude during the simulation, run a nonlinear geometric solution. Predict the load path before running your model. Make sure you don't generate an overstiff or understiff problem when you define your boundary conditions. The boundary conditions usually generate singularities, so keep them far from the region of interest. Finally, the last suggestion I want to share with you about defining the correct loads and boundary conditions. Check at the rigid body motions and mechanism. Again, here it is as simple as reading the output file, the log file, or plotting, creating a deformation plot. To conclude with boundary conditions, let me share with you the 7 questions you should answer to successfully define your boundary conditions. By answering these 7 questions, you ensure that your boundary conditions are realistic, representative, and lead to accurate FEA results. Proper boundary conditions help avoid rigid body motions, artificial stiffness, and incorrect stress distributions, which are common mistakes in structural analysis. Always validate your choices with physical intuition or test cases. Boundary conditions must reflect how the structure is supported in reality. Misrepresenting the support can lead to incorrect stress distributions and unrealistic deformations. So, identify all the points where the structure is physically supported in the real life. They can be physical constraints like bolted connections, pin joints, foundation support, or even elastic support such as rubber mount, for example. Consider the type of support: fixed, simply supported, roller, hinge, or a combination of them. Account for distributed constraints. For example, a beam resting on a flexible support should not be modeled with a rigid fixed constraint, as this should alter its deformation behavior. Check for real-life flexibility in supports. If the structure rests on a surface, is it rigid or elastic? Okay, answer this question. Do you need to model a foundation with spring supports? It's very important to answer this question in order to define proper boundary conditions. The degrees of freedoms define the ways in which a structure can move. Okay, so answer this question. What are the degrees of freedom of your structure in reality? A 3D solid element typically has 3 translational degrees of freedom per node, the 3 directions x, y, and z. A beam element has 6 degrees of freedom per node, 3 translational and 3 rotational. Shell elements allow for bending, meaning they may also have rotational degrees of freedom. Some components may experience constrained movement due to their connection to other parts, limiting certain degrees of freedom. So, understanding the actual degrees of freedoms of your structure will help ensure that unnecessary restrictions are not imposed to your model, which can lead to over-constrained model and unrealistic stress predictions. If you apply a certain set of boundary conditions, answer the question, do you allow or restrict the degrees of freedom that exist in the physical system of your modeling? And this is a critical validation step after defining boundary conditions. Over-constraining or under-constraining can cause numerical errors or even incorrect results. Over-constraining the model can lead to artificially stiff structures, unrealistic stress concentrations, and an incorrect load path. On the other hand, under-constraining the model may cause a structure that exhibits rigid body motion, leading to solver errors, such as singular matrices in implicit solvers. So you won't be able to obtain a solution. The best practices are to check for unintended constraints by running a free model analysis. That I was talking about that in the first part of this series, to see if unexpected modes appear. Okay, so ask yourself, am I restricting a movement that should exist, or am I allowing a movement that should be constrained? Sorry. The fourth question is, where are the loads applied in the structure? The loads must be placed exactly where they act in the real life to ensure accurate force transmission and stress distribution. So the point loads versus distributed loads, it's a very important concept. Applying a force at a single node can lead to unrealistic stress concentrations. It may be better to apply the load over a surface or distribute it among multiple nodes. There is also the concept of offset loads. If a load is applied at an offset, it induces moment. This should be included in the model to avoid underestimating stresses. There is also the concept of dynamic loads. If the load is time dependent, consider transient or frequency-based approaches. The fifth question is, what types of load are applied to your structure in the real world? Identifying the correct type of loading is crucial in defining accurate boundary conditions. First, we have the static loads, like a concentrated force, a uniform pressure, the gravity, a thermal expansion, a thermal loading, etc. You can have also dynamic loads, impact forces, harmonic loads, random vibrations, or fatigue loading. It can be also a pre-stress effect. Loads such as bolt preload or residual stresses from manufacturing, like welding, forging, or when you close a gap by tightening a fastener. You have also the nonlinear loads, loads that depend on deformation, such as the follower forces. So ensure that the boundary conditions allow the structure to react to the applied loads as it should be in the reality. The other question to answer is, can you remove some parts of your model, replace them with boundary conditions, and still produce a realistic representation. Many times, parts of the structure do not need to be explicitly modeled if their effect can be represented through appropriate boundary conditions. Let me give you an example. Instead of modeling bolts and washer explicitly, you can apply bolt preload and appropriate contact boundary conditions. Another example is symmetry considerations. If the problem exhibits symmetry, only a fraction of the structure may be modeled by applying symmetric boundary conditions. There is also equivalent stiffness representations. If a rigid component is not crucial to local stress analysis, it may be replaced with appropriate constraints or springs. However, when doing that, be careful not to oversimplify the model to the point that essential physics are lost. The last question to answer in order to define correct loads and boundary conditions is: does your structure exhibit contact between some parts? Contact introduces nonlinear behavior in your simulations, significantly affecting the response of the model. So the types of contact is very important. Is it a bonded, a frictional, a sliding, or separation contact? You need to consider that. There is the concept also of rigid versus deformable contact. Some contacts may be modeled as rigid to simplify the calculations, but you have to justify that. If you are not able, it means that you have to consider a deformable body. There is the concept also of contact stiffness. Too stiff contacts can introduce artificial stress concentrations, while too soft contacts may result in unrealistic deformations. There is also the contact detection concept. You have to ensure that the mesh is refined enough for the accurate contact force distribution. If your structure has significant contact interactions, selecting appropriate boundary conditions to complement these interactions is critical. So, to conclude and summarize this section about building the model, here are the 14 questions I like to answer before to begin modeling. I like to answer them before I start my modeling process because they permit me to do the right assumptions at the beginning of my modeling process. The first question is: have you clearly defined the model goals? Every simulation should start with a well-defined objective. Okay? What are you trying to learn or demonstrate? Are you focusing on stress analysis, deformation, stability, vibration, or failure prediction? Will the results be used for design validation, optimization, or certification? Are you looking for qualitative trends or precise quantitative results? Defining the goal guides all modeling choices, from element type selection to boundary conditions. The second question: which solution do you plan to use? And is it consistent with your problem? The solution method should match the physics of your problem. Consider static or dynamic, linear or non-linear, implicit or explicit. Static or dynamic: if loads vary with time, transient or frequency domain analysis may be necessary. Linear or non-linear? Non-linearities such as material, geometry, contact require different solvers. For implicit or explicit, it's very important because explicit solvers are good for impact and crash simulations, while implicit solvers handle static and low speed problems more efficiently. So choosing the right solver impacts accuracy, convergence, and computation time. The third question, do you trust the geometry you plan to use and can you change it if necessary? Geometry plays a crucial role in the FEA accuracy. Before meshing, verify if the geometry is clean, okay, without unnecessary details that may complicate the meshing. Do you need to simplify or defeature the geometry? For example, removing the fillets, the small holes, the thread, stuff like that. Or all the parts and surfaces correctly defined. Can the CAD model be modified if necessary? A poor quality geometry leads to meshing problems and unreliable results. Another question to answer is, can you justify your choice elements? The selection of elements, solid teeth, solid eggs, 2D shell, 1D beam, etc., affects both accuracy and efficiency. So you have to consider the dimensional consistency. Should you use solid, shell, or beam elements? The aspect ratio and the quality. Avoid elements with high aspect ratios or the distorted elements. The concept of order of elements. Are linear elements sufficient? Or do you need quadratic elements for better accuracy? The mesh quality. Are you refining the mesh where the stress gradients are high? Okay? So, element choice should balance accuracy, convergence, and computational cost. The question 5 is, which boundary conditions will you apply to your model? And why did you select them? As I said before, boundary conditions must reflect the real-world constraints. So consider, where are the supports? Are they fixed, pin, elastic? Are you applying symmetric and anti-symmetric or cyclic symmetry conditions? Have you prevented rigid body motion while keeping realistic constraints? And do the boundary conditions allow all realistic degrees of freedom? Question 6. Do you understand perfectly the loading you will apply in your model? And it is related to the previous question. Okay? The loading condition should match the real world in terms of force, pressure, displacement, and stuff like that. Okay? Unrealistic loads can invalidate the entire simulation. Question 7. Have you identified the major load path in your structure? Understanding the load path helps predict the stress concentration areas and the deformation trends. Okay? How do loads transfer through the structure? You have to know that and answer this question before to start the modeling. Where are the stress concentration if you expect to have some? Okay? A solid understanding of the load path will help optimize the meshing and the result predictions. Are you able to anticipate the response of your structure? Before running the simulation, you absolutely need to know where do you expect the maximum stress or the maximum displacement. Okay? Will there be buckling or yielding issues? And if nonlinearities exist, how will they impact the result? Okay? At which locations in the model do you plan to extract the results? So plan ahead on where to inspect the results. So the stress hotspots, the critical deformations, the critical zone like the high stress regions, and the reaction forces to verify equilibrium and ensure there is no error in how you constrain the model. Another question to answer is, which accuracy of results do you require? Accuracy requirements influence mesh refinement, solver setting, and model complexity. High accuracy requires refined meshing. If qualitative trends are enough, a coarser model can be used. Also, are experimental and analytical results available for comparisons? Okay, answer those questions. The question 11 is, have you identified all the modeling techniques you will use to build your model? Choosing the right modeling techniques is crucial for achieving an accurate, computationally efficient, and well-validated FEA simulation. This step influences element selection, mesh strategy, simplifications, connection modeling, and the handling of complex behaviors like contacts and material nonlinearities. The question 12, have you identified discontinuities in the structure you wish to model? Because discontinuities such as sudden cross-section changes, for example, like the sharp corners, the notches, the fillets, will influence the results of the simulations. Also, the joints and the connections where stress concentrations may occur. You need to identify them, okay, in order to do the right choice in the modeling technique. And these areas are often need, often need local mesh refinement to capture accurate stress concentrations or stress distributions. The 13th question is, have you identified all the capabilities and limitations of your model? Understanding the model limitations help you interpret the result correctly. And every model has limitations, okay? The computational limits. Do you have enough resources to run a fine mesh or a nonlinear analysis? The software constraints. Can you solve under can the solver handle large deformations, contact, or plasticity? Expected approximations. What simplifications may affect the accuracy? Being aware of limitations prevents misinterpretations of results and doing wrong assumptions when you build the model. The last question to answer is, do you expect any potential sources of nonlinearity? Okay, nonlinearities, as I said before, affect convergence, computation time, and result accuracy. So the key sources include material nonlinearity, plasticity, hyperelasticity, for example, geometric nonlinearity like large deformations, post-buckling behavior, and contact nonlinearity, the surface interactions, friction, separation. If nonlinear effects are expected, ensure that solver setting and element formulations are appropriate. And if you don't expect those kind of nonlinearity, go with a linear solution. It will be simpler and enough for you. If you cannot answer all of these questions, do not start the modeling process. By answering these 14 questions, you establish a strong foundation for your FEA model. This approach minimizes errors, improves efficiency, and ensures realistic results, leading to better design decisions and confidence in simulations. So see you for the next part of the series, Creating Your FEM Right the First Time, which will be dedicated to solving the model. Don't forget to like, share, and subscribe to the channel for more content. And feel free to contact me on LinkedIn or via email. Thank you.